Hi, we're Miami University. Obviously, our district use case was the Pacific Northwest National Research Laboratory. I do not have control of your screen. Oh, there we go. Did you give me control of your screen?
I approved it. Do you want to try requesting it again?
Yeah.
Okay, approve. Sometimes you have to click into the space first and then.
Okay, there we go. I'm sorry.
All good.
Okay, and then a quick introduction of our team. My name is Michaela Pandorf. I worked on the conceptual design. We also have Jarrett Braun. He was responsible for our financial analysis. Beth Henderson worked on our distribution approach, and Dominic Vo was responsible for our development plan. And we are all senior mechanical engineers. So first, I will walk you guys through our proposed system design. First, in our primary challenge area, we have a 1.6 megawatt ground mounted PV system kind of down here, if you can see in our south ground mount. And then we also have an 880 kilowatt roof mounted system up on the EMSL building. Additionally, we have two 2,000 kilowatt hour battery banks. And in this challenge area, we have 3 buildings with critical loads to be sustained, and our conceptual system design is capable of meeting these needs. And then in our secondary challenge area, we have a 1.4 megawatt ground mounted PV system with one 1,200 kilowatt hour battery bank. And we also have 2 buildings with critical loads to be sustained in the secondary challenge area. And our battery bank is also capable of meeting those needs as well. And then our South Campus roof mount, we have SunPower E-Series panels up on this roof. We have about 2,000 panels and 56 Fronius CMO inverters. We selected this area because of the high irradiance levels up on this roof, and all of our panels are placed in an area where there's minimal shading. This large flat roof is ideal for a large PV array. And we also have these walkways for maintenance that is compliant with Washington State's codes and regulations for these things as well. So maintenance workers are able to access these solar panels. And then in our South Campus ground mounted system, we have about 3,600 panels, 91 inverters, again, the SunPower E-Series panels. And then this space is large, it's open, and it's offset from this tree line to avoid any shading issues that could be encountered there. And then this is very visible to the public. We selected this on purpose so visitors and employees at the campus would be able to visually see PNNL's commitment to sustainable energy. And then these walkways are also accessible to cars. So if a maintenance truck needed to drive through them, they would be capable of doing that. And then our third array up in our secondary challenge area, we have about 3,200 panels, 99 inverters. This is a large flat area with no shading issues. As you can see, there's not really any trees to worry about up in this area. And then we have walkways again for maintenance. And this is also visible to the public like our last array we had. And then this is our annual production data from all of these panels combined together. During peak production, in about July, our proposed array is capable of meeting about 92% of our campus's energy needs. So that would utilize the rest of that low-cost hydroelectric power to fill in those needs. And then this is a chart of our system's energy production. As you can see, we're peaking at about July, as would be expected with a system like this. And I will let Beth take over for the distribution system.
So there are several considerations that factor into the PV hosting capacity, which we needed to make sure that our system would be under the constraints of those. And those include voltage, thermal, protection, and line constraints. So ultimately, heat maps were used to assess the capacity, but other mitigation measures were considered and just kind of built into the design. And those risks are low since we're not exporting any energy to the grid. But other mitigation measures that we considered in our design included minimizing environmental factors that could cause voltage fluctuations, and taking into consideration when thermal conditions would be the highest, such as in the summer. And the storage also provides load balancing, and we wanted to minimize the distance of transmission for to mitigate those line constraints. So here is the map of where you can see in the red outline are the buildings that we were provided load data for. So those are the buildings that we're trying to provide the energy for. And our arrays are outlined in blue. And you can see that the EMSL building is kind of centrally located on that map. So it is proposed to directly wire the roof mount there to the EMSL building because it could provide up to 40% of its energy needs alone. And we also have our ground mount down in the south area of campus. So we can either directly wire to those buildings, which would provide more energy resilient operations, but also using the heat map where it can be seen that in the areas where the energy can be distributed to more branches on the grid, there's a lot more capacity there. So by interconnecting to the grid in that location, it would even further reduce any of those risks, such as reverse power flow, reduce power quality, or power loss. And in the secondary challenge area, there was a lot of potential for a large ground mount because of all of the open land space available. So it's a relatively large array compared to the energy needs of this section. So this area in particular, it would be beneficial to connect within the grid rather than directly wiring to the buildings.
So for the financial model, we needed to ensure that the system was going to be financially beneficial for PNNL, which is a tough task because they already get their energy from hydroelectric source, which is one of the cheapest kilowatt hours that can be purchased throughout the country right now. And so developing the financial model started with baseline assumptions that were provided to us in the rules. And then along with these other assumptions, we had to make other assumptions about the system and other components that would be factored into the financial model, such as the cost of labor, how much that would be, the bill of materials, and then the type of purchasing agreements that could be done, whether it's a PPA or an SREC. And so those were all taken into account for building the financial model. So these is just a quick snippet of the part of our financial model that we did in Excel, where we got construction costs per watt. And then we also made other assumptions, such as whether the person or the owners of the project would be needing a loan, if they'd be able to take advantage of the ITC, and then just other options like if a PPA would be a viable option or if the SRECs would be a viable option. So in general, throughout the duration of its life cycle, we expect a total savings to equal $5.7 million with the PPA price at 6 cents, which we believe can be even higher because we tried to match the price of their current energy supply, which is at 4.17 cents currently. The only downside is the return on investment is a little longer, unfortunately, which is set to hit in about 12 to 13 years time. But that's understandable because of how cheap their current source of energy is already.
So when designing the initial development plan, from the two images we can see above, we can see the locations of all three of the proposed arrays, as well as the two locations for the battery storage. And so each of these locations were cross-referenced with PNNL's future campus master plan, just to ensure that no designated spots would be interrupting any future operations, as well as the team needing to identify land, code, zoning, and regulations that needed to be accounted for during the making of the development plan. So from the figure on the right, we can see the area of restricted use that the DOE plans on using as a possible relocated route for Navy Hall Road, which is a road that the Navy would use to transport naval reactor compartments. It was an important component that the DOE reserved an 31-meter wide, I believe, corridor for that purpose, as well as on the right, we can see gateway and staff core areas being planned for remote synergy and interaction within the PNNL community, as well as other areas that are not shown included the future common use and open spaces. So all these spaces were ensured that they weren't interrupting any of our potential locations for the PV system. And then due to the fact that one of the proposed arrays fell under land that is federal US Department of Energy owned, more regulations had to be accounted for, which we can see above. Some of these include the Executive Order 13834, which is just for requirements enacted by Congress relating to energy, or the Energy Policy Act of 2005, as well as Articles 690, 691, and 705 of the National Electrical Code, which were all major ones that we accounted for during the initial design. And then this is just a potential construction timeline for the PV system, which should be aimed to be completed in around 7 months. And some of the innovative ideas that we used for the PV system were heat maps utilized in areas of interest in order to optimize energy efficiency, as well as ensuring we were choosing the best possible components in the market, such as Fronius inverters. We found that some power modules were a favorable company, as well as the Simtech Megatron battery storage. So why choose Miami University? We achieve resiliency goals. We offer the best possible cost-benefit ratio. We incorporate both functional and aesthetic designs, and the designs were exclusively designed by engineers.
And that's all from us. We'd be happy to take questions at this point.